Hello everybody, I am Ben from Team Panic, and today we are back on the Melty Brain. And last time we were here, we were looking at all of the wiring and everything, and I was talking about how I was having a lot of problems getting the accelerometer up and running. And well, the accelerometer is still in the naughty corner. So today we're going to try and get the Melty Brain spinning up without any sensors at all. Now, this should be 100% possible. It's just probably not going to be quite as accurate as having no sensors, but a spinning and moving Melty is going to be way better than a not spinning and moving Melty. So we're going to try and do this with odometry, which is essentially maths-based guessing of the position of the Melty Brain. But how does that actually work? So it's kind of simple and it's kind of not. Basically, at the end of the day, what we need to know is how fast the Melty Brain is rotating. Initially in RPM, but then we'll have to convert that down to a number of degrees per millisecond that the robot is spinning, because then we can use a clock in the actual controller for the thing, and we can work out how many milliseconds it's been since the last time we read the timer, and then we can kind of times that by our speed of rotation to work out how many degrees the robot has theoretically moved since the last time we read the timer. So what we need is that RPM of the Melty. That's what we need. This is our end goal. But what we have right now is not even an RPM, we have a kV rating. So we have the kV rating of these brushless motors in here, which have no gearbox on them, so they're literally just straight into these wheels. So our kV rating is 380 kV, which is RPM per volt. And we're going to be running off of a 12 volt battery, a 3S battery, which is 12.6. Now, this value here will actually get the controller to read, so it can update the speed of these motors on the fly, but we're just going to put 12.6 in here for the time being. So we know that the speed of our motors, or the max speed of our motors, is 380 times by 12.6, but the overall speed of our motors, so RPM motor, is 12.6, or 380 times by 12.6 times by the throttle percentage. So this is the value that we feed into the speed controller to tell the speed controller to spin the motor at a certain speed, right? So the throttle percentage is going to change how fast the motor itself is moving. So now we've got an RPM of the motor, which is a good start, but that's not the RPM of the Melty. So the next thing we can look at is the actual Melty itself. We can see we've got two wheels here, and they, if you look at it, are essentially a gearbox to the size of the Melty itself, right? So this wheel, as the whole thing spins around, this wheel rotates around a circumference, and it has a circumference itself. So a certain number of rotations of this wheel will result in one full rotation of the Melty itself. So we can basically essentially say that these are a gear ratio. So what we need to do is measure the wheels and then also their distance apart inside the Melty. Okay, so with that done, we had a diameter of 72 millimeters for the wheels and an approximate diameter of 121.85 millimeters for the Melty itself. Now that's because we have a measurement of the outside edges and a measurement of the inside edges, and I've just halved those, or times them together and added them together and halved them to kind of get the approximate center of these wheels. That's probably not going to be accurate because it's very unlikely that the Melty is running exactly on the halfway point down these wheels, but it's a good approximation to start with here. So if we get those like this and go like this, 72, so this gives us our ratio of motor speed to RPM Melty speed, so that ratio is 0.59. So what we can say from all of this is that the RPM of the motor is, the RPM of the Melty is the RPM of the motor times by 0.59, which means that this is not even a half reduction on the actual melty itself. So that's pretty interesting. These motors aren't getting that far reduced when they're spinning this melty up, which is kind of terrifying. So I'm just going to throw some numbers into this, and I can tell you that all going well at 100% maximum on everything, assuming that there's no air resistance and whatever else, we should be able to get 2,824 RPM out of this melty. That's insane. That is a massive, massive speed out of this melty. All right, well, that's crazy. So now we're going to actually plug that into this and we're going to try it out. Now, I do have one little thing up my sleeve here as well, and that is basically we're going to take this RPM value and we're going to turn it into a degrees per millisecond value. But what I'm actually going to do is I'm also going to add an extra input in here. Because what I'm going to try and do is get this to spin up, like I said, on its own without a sensor, and I'm pretty sure that this calculation, there's going to be some errors in it somewhere. Either this throttle percentage is going to be wrong, or this diameter where the wheels sit is going to be wrong. Something is going to be wrong, so I'm going to put another input on my controller that I can use to fine-tune the speed that the robot thinks it's going, which should hopefully allow us to get the heading light pulsing just perfectly on the 0 degree point. So I'm going to do that. I'm also going to sit down and clean up the electronics, because last time you saw them, there was a breadboard in place and we really, really can't do that. So I'm going to do a bit of that stuff and then we can have another look at it. Okay, so that was a lot of maths. And where does that get us? Well, not very far. I basically put that maths into our microcontroller, plus a little bit more that converts RPM down into a time range that the microcontroller can read, and then it also reads that amount of time range and then increments up a counter that tells the robot where it is in a revolution. And I've also added just a little bit of code that turns this light on when the robot thinks it's between 0 degrees and 15 degrees, and between 360 degrees and 345 degrees. So it's kind of like a 30-degree arc right at the front of the robot it will turn the light on for. So we've also got the melty up on chocks at the moment, because it does actually spin the motors up when we do this. So let's take a look at how all of this stuff goes. So first of all, we're going to turn the controller on, because we are doing a wheels up test, so we want to just make sure everything is as safe as we can have it be. So if I throw the battery in here and nothing spins up, that's good. All right, so we're on track so far. So we'll throw it into melty mode. You'll see that nothing down here changes right now. We actually need to get the wheels spinning up. So you can see that this light is flashing at a certain rate based on how fast the wheels are going. So if I crank the speed up, you'll see that the light flashes faster, and if I crank the speed back down again, the light flashes slower. So that should, once we get everything packed in, indicate our forwards heading. Now I've also got this other switch which allows me to change the speed of the flashing based on this other switch, so I can actually kind of hone in on the actual speed that the robot is going while it's spinning up. So we'll just stop that for half a second. But I do have another problem here, and that is one of space. So if I'm just going to unplug everything for a second. So if we look at the melty at the moment, this box is pretty well taken up by just these ESCs. These ESCs are a little bit big, and then they've also got pretty much all of their wiring attached to them as well. So this whole front box is essentially just ESCs and some power distribution wiring. So that's, I mean, not very good. We need to do a lot better than this eventually, but that means that there's really not any space for all of our brain components. So we need to fit them somewhere. And I'm thinking that we're going to fit them in the other side, because you can see the battery Doesn't take up all the room that's over here. It does take up a good chunk of it, but there is some room around the edges here. So what I'm hoping is that we can squeeze the brain electronics in around the battery over here, and if we can't fit it in with this battery, then I'll have to find a different battery and hope that I can get that working. So yeah, we're going to try and route all of the wiring across over there and make this work. Fingers crossed. Okay, so here we go. I have my Lexan screen between me and the robot, so it might be a little bit blurry, but hopefully this will all work out all right. I decided to leave the electronics in the side I wanted them, so they've just been kind of duct taped in for now, so we're going to go pretty slow because I don't want them to go flying everywhere. This is just that first test to see if we can get the thing spinning at a decent speed, so we'll flicker over into melty brain mode and give this a shot. Well, that's not working. I'm getting dual images, so the light is not flashing where I need it. Oh, okay. We hit something. Interesting. Let's flick it back a mode. Yeah, we're a little unbalanced too, which is why it's moving towards the screen. I'm gonna have to try this again, I think. Stabilizing. Ah, yes! Yes, yes, yes! No, come on, go back to that. Oh, come on! No. Alright, that's enough. That's enough. So that's going okay. The whole robot is definitely out of balance. The front electronics stack up down here is definitely heavier than the battery, which is actually not something I was considering. And that kind of imbalance is what's causing it to translate as I'm trying to sit there and tweak it so that the light heading stays correct. Because that's what all I'm aiming for right now, is just that light to stay facing in one direction. As long as I can do that, then we'll be golden to move on with this thing. But yeah, so the weight destabilization that's going on is a big problem because it's causing the thing to move, and it's also meaning that every now and again it's like rocking a little and hitting the ground and becoming really, really unstable, which is not good. The other problem that we're having too is that these wheels slip. which means that our odometry calculations are just, they're not right at all, because so the fact that the wheels are slipping means that the wheels will be going faster than, yeah, and the melty will be going slower than what we've calculated. So there's not really much I can do about that for now. I might need to do better wheels, but we've seen in the past that the silicon wheels need to be really, really firmly attached to the melty, because otherwise they just come flying on off. One thing I can do for now is tweak my controller settings, or actually tweak the settings in the brain itself, because at the moment we've got a little bit of a reduction on my signal going in that tweaks how fast the robot thinks it's going, and that means that I've actually been maxing this dial out and still not getting to exactly where I need to be for the heading. So I've done a few little bits and pieces. I've changed the code in here so that the reduction on the dial is no more. And well, actually it's turned down, it's not no more. I've also rebalanced just a little bit, and we'll try this again. Hey, we are getting pretty close now. That was very, very exciting. So obviously there's a couple of points where the speed of the motors and everything gets to just this right point where everything balances out and it spins really, really smoothly, which is awesome. I really like that and really like to see that. And when it's spinning smoothly like that, I can tweak it so that we get a heading that's perfect. And what it seems to be is that at the lower speeds, it has more trouble finding, or I have more trouble with my controller finding a nice heading than I do at higher speeds. But higher speeds are really scary with an unstable design right now. So We've got a good start. We've got a nice start on a heading, and we've got some, yeah, it looks like it's going to work. The thing that I now need to do is go through and rethink all of my component choices, basically. I need to have smaller ESCs, smaller connectors on my ESCs, and maybe less connectors in general. I'll probably build a PCB for the electronic stack up because it is quite large and messy right now. And we could shrink all that down onto a PCB and it would work a lot better, I think. Yeah, and then we're also going to have to decide how we get our weight to work correctly, because at the moment, like I said, the battery is lighter than the electronic stack up, and we've still got 2 more ESCs to go so that we can get the spinning weapons on either side. So I've got some hardware decisions that I need to make, which means I'm going to have to order some parts. It's probably going to be another like 2 or 3 weeks before I get those in, because everything is still quite slow in terms of getting parts and different bits and pieces. But that's going well. That's a lot better than I thought it was going to be at the end of this video. So yeah, we're on the right path. There is something that I might try. I've just got a kind of crazy idea for another way that we could maybe find a heading. And if that works, then we might even be able to find a heading exactly as the robot stands right now. But I don't know, so that might probably be a couple of weeks away before we'll have a look at a different idea on finding a heading without using that accelerometer. Because at this point, I'm going to try everything else before I go back to the accelerometer, or at least I'm going to try a lot of different things, and then if we go back to the accelerometer, it will be used in conjunction with something else, so that it's easier for me to make sense of whatever the accelerometer dishes out. Anyway, that is going to be it for this video. I hope you guys enjoyed that one, and I will see you in the next one.